We are in Chapter 1, Section 2, where we are discussing stress and axial loads. This is the 7th session overall and the 3rd session in Section 2. Here, first we'll discuss more examples on normal and shear stress, and then we'll discuss stress in oblique planes. Again, is an overall view of the sessions we are covering at this stage. And we are now in the 7th session, which is in the middle of Section 2 of Chapter 1. Whenever a group of forces act on a body, they vectorially add up to 0 or vectorially add up to a resultant, or they create a couple. Here the tension in the rope remains the same at 600 Newton. So on this body, there is a force of 600 Newton here and a force of 600 Newton here. So these two forces create a couple. A couple has to be negated by another couple. So in this body, the reaction forces must come from C and B. C is a link, so we know the direction of force that will act on C. As such, the force in B must have the same direction, and these two forces create a couple to balance the couple created by the tension in the rope. We have to find out the moment arm, and the moment arm is found out using this diagram, and we get it as 237.46 millimeter. Divide the moment by the moment arm, we get the force R, and dividing it by the area of the link, we get the stress in the link. Here we consider another example. This is a bar AD with a hinge at C. It has a roller support. There are three forces acting, transverse forces, and one of the forces acts at the hinge. There's also this rod which is connected with that bar. Earlier we had a problem which we solved as a plane truss. This problem to be solved as a plane frame, even though we have only horizontal and one vertical member. In plane frames, we look at the equilibrium of members. So here we have to look at the equilibrium of CD and AC. So in a plane frame, if you had a hinge at M, then one force was due to bar 1, and opposite force was due to bar 2. And due to these two forces, M, the hinge M would be in equilibrium. The hinge C in turn exerts equal and opposite forces to the two members CB and CA. In this case, there's no horizontal forces. So there would be two forces opposite to each other in the vertical direction. So, and we choose arbitrarily the direction. So here for CD, we have taken RC acting vertically. In ABEC, we have RC acting in the downward direction. There's a load of 10 kilonewton acting at C, and we could have taken the load as part of CD or part of AC. We have taken the load as part of AC. So this load is RC plus 10 kilonewton. Considering the equilibrium of the part CD, we can find RC and RD. And once we have found RC, then we know these two forces, and we can find RA and RPE. Now, this force RPE is due to PE acting on ABEC. So the force that ABC exerts on PE would be in the opposite direction. So PE would be in tension. So we are required to find the stress in PE. So we have found the force and divided it by the cross-section area to find the stress. We have looked at shear in bolts and shear in pins. Here we look at shear through plates. So this is an arrangement of plates of which a cross-section has been taken. The dark section is steel and this portion is circular. Also, this hole is also circular. The light portion is aluminum. A load is applied here and we are required to find the maximum load that can be applied. So this arrangement will fail either by shearing through steel or by shearing through aluminum. If it fails by shearing through steel, then this part would shear. If it fails by shearing through aluminum, then this part will shear. We are given the allowable shearing stress in steel and aluminum. To find out the ability of the steel portion to withstand the load, we multiply the allowable stress in steel into this depth 15 millimeter into 2 pi r, that is the circumference of the circle whose radius is 10 millimeter. To find out the strength that the aluminum portion can withstand, we multiply the allowable stress in aluminum, that's 100 MPa, multiplied by the depth 10 millimeter into the area 2 pi r of the circumference of the circle, where r is 40 millimeters. It is found that the steel portion will shear first. Hence, the maximum load is given by the capacity of the steel portion. Consider another example. This is an arrangement. AC is a wire and AB is a bar of dimension 60 by 20 millimeter. A load P is applied here and we are required to find what is the maximum load that can be applied. We are given the strength of shear stress, maximum shear stress in the pins B and C, and the maximum bearing stress that AB, the bar, can withstand. This angle is given as 30 degrees and the length is this is 1 meter and this is also 1 meter. To start with, we look at some geometry. So if this is AB and if we take a point D here, then this is 1 meter and this is 30 degrees. And now the whole arrangement here, this is AB and this is AC. This angle is 30 degrees. So this angle ABC would be 150 degrees. This is 1 meter and 1 meter, so this is isosceles. So both these angles would be 15 degrees. If this angle is 15 degrees, since this is 30, this is also 30, then this angle would be 15 degrees as well. The load here is applied at joint A, and so we can solve this problem by considering equilibrium of joint A. So we consider all the forces in the vertical direction and in the horizontal direction first. So F1 cos 15 degree plus F2 cos 30 degree is equal to 0, from which we get a relation between F2 and F1. Also, solving for the vertical direction, F1 cos 75 plus F2 cos 60 plus P is equal to 0. And now using those both equations, we get F1 is 3.346P and F2 is minus 3.732P. So we are more interested in the force in F2. Now for F2, so that the pin does not fail, we consider the stress that the pin will be able to, shear stress that the pin will be able to withstand, which is 200 MPa, by the area of the pin. That is equal to 3.372 P, from which we get P is 30. Now considering bearing failure, diameter of the pin is 20 and the thickness T of this bar is also 20, multiplied by the bearing stress, maximum bearing stress, allowable bearing stress, then we should get 3.372 P, from which we get P's. So the arrangement would fail by bearing first. We earlier considered cases where a bar was subjected to normal stress only, or a bolt was subjected to shear stresses only. So with structural components, we have considered either normal stress only or shear stress only. Here we'll be looking at cases where both normal and shear stress act at the same time. Consider the cases of bars we have been dealing with. So this is a bar subjected to a load, tensile load, and a cross section is taken perpendicular to the axis. Then cross section is subjected to normal stresses as shown. This is a case where a shear force acts and this horizontal section is subjected to shear stresses only. We'll now consider oblique planes in a bar subjected to a tensile force, and we'll see that these oblique planes are subjected to both normal and shear stresses. Here we found out the normal stress to be P divided by the area. So we'll find out the magnitude of the normal and the shear stresses in the oblique planes. To start with, we need to designate a rotation as positive, and we consider counterclockwise rotation as positive as shown in this diagram. Here we consider normal and shear stress acting on an oblique plane in a bar subjected to axial loads. We had previously considered sections perpendicular to the axis for bars subjected to axial loads. Here, this is the whole bar. We have taken a plane that is theta degrees to the vertical in the anti-clockwise direction. We had earlier considered anti-clockwise rotation as positive, so this angle is positive. Consider the left hand portion of this bar. Since there's a load P acting here, there must be an equal and opposite load P acting on the right side. This force P can be resolved into a force F perpendicular to the section and a force V parallel to the section. If the area of the perpendicular section is A, then the area of this inclined section is A divided by cos theta. Now let us find the forces F and V. Since this angle is theta, F is equal to P cos theta and V is equal to P sin theta. Then the normal stress on this section is equal to F divided by the area of this inclined plane, which is F divided by A by cos theta, is equal to P divided by A cos square theta. Tau is given as minus V by the area of this inclined portion, which is A divided by cos theta. So we get tau as minus P by A cos theta sin theta. The minus sign in shear stress is related to the fact that we take upward shear stress this plane as positive. You can see from this equation that the normal stress will be maximum when cos square theta is equal to 1 or theta is equal to 0, which corresponds to the normal perpendicular section. So the normal stresses in this perpendicular section is the maximum normal stresses we will get. Initially, the state of stress at a point in a body subjected to loads were given using a three-dimensional infinitesimal element. We designated the stresses on the faces of the element. Later on, we discussed that the stresses associated with the z dimension is normally 0, and as such, the stresses can be given in 2 dimensions. On the other hand, we took simple cases of loading and took sections and found out the stresses on those sections. So in an axial loaded bar, we considered a section perpendicular to the axis and found out the normal stresses. We also found out the shear stresses on a section in a bolt. In the last slide, we discussed stresses on a section that is oblique in a bar subjected to tensile loads. So on one hand, we had discussed elements, while on the other hand, we have discussed sections and stresses acting on it. Here we relate the two. So we give the stresses acting on the elements on the sections that we have considered. Then we see how the stresses in the elements varies as the section rotates. Here we continue our discussion with the bar subjected to tensile force. We consider a section perpendicular to the axis, which here is given as C1. We consider a point in the section. We take that point as the centroid of the section. However, it is not necessary to take a point which is the centroid of a section. We could have taken any other point for our discussion. Initially, we considered the stress of the element at that point when one of its sides is aligned with the cross-section C1. Then we consider oblique sections at different angles as shown here, all passing through the point C. The element at C is rotated so that the base of the element coincides with the oblique plane. We find out how the stresses acting on the element varies. For a perpendicular cross-section, we have earlier found out that the stress acting is P divided by A, where A is the area of the perpendicular cross-section. So the stresses on this element is as given in this figure. A sigma x of P divided by A acts on the face where it is aligned with the cross-section C1. And for equilibrium, there will be another stress sigma x acting on the opposite face. There are no other stresses acting on the element. Now let us consider this bar with the oblique cut. So this is the portion of the bar to the left, and this portion will be in equilibrium. So if a force P is acting here, there will be a force P acting on the right hand side. We can resolve this force P into F1 perpendicular to the section and V1 parallel to the section. F1 divided by the area of this inclined section gives sigma x, and V1 divided by the area of this inclined section gives tau xy. This element is shown here magnified and upright. This oblique plane is shown here. So we have just found out sigma x and tau xy. For equilibrium, there would be sigma x and tau xy acting here. These two tau xy form a couple And to balance the couple, there must be a tau yx acting or two tau yx acting. We have earlier seen that the magnitude of tau xy and tau yx are the same. So this gives us all the stresses apart from sigma y. To find sigma y, we pass an oblique section that aligns with the top face of the element here. Again, this portion is in equilibrium, so there must be a force P acting, and that force P can be resolved into a normal force F2 and a force parallel to the surface V2. F2 divided by the area of this inclined plane will give us sigma y. We have taken this angle as minus 30, minus because it is clockwise from the vertical. Putting in the values of theta, we get these as the stresses acting on the element. We consider a plane here that is 45 degree clockwise to the vertical. So the angle is minus 45 degrees. As earlier, this portion of the bar has to be in equilibrium, so there must be a force P acting on this side. This force P can be resolved into a normal force and force along the plane. Dividing the normal force by the inclined plane area, we get sigma x, and dividing the force parallel to the plane by the area of the plane, we get tau xy. This small element has been represented here with this oblique plane represented by this vertical line. We have then found sigma x and tau xy. As earlier, considering equilibrium, the stress on the other face has to be the same, and the shear stress also has to be equal. These two shear stresses cause a couple which must be balanced by a opposite couple, which is comprised of tau yx. We earlier found out that tau xy is equal to tau yx in magnitude. So we have all these stresses except sigma y. In order to find sigma y, we consider a section which coincides with the top of this inclined element. The force here must be P, and we consider a normal force and a force parallel to the section. P is resolved along the normal of this section to get the normal force, which when divided by the area gives us sigma y. So here we have represented sigma y. This is another case, but here we have taken a positive angle. So the angle is anti-clockwise 30 degrees to the vertical. Here we get a shear stress which is in the opposite direction of the earlier two cases. So the shear stress on this plane is negative. Tau yx here produces an anti-clockwise moment and is positive. Thus, Here we see that we can keep on rotating the element and doing sections, and the normal and shear stress will keep on varying.